Hi everyone, welcome to our workshop. So in this workshop, we'll learn about LLM agents. And typically we have a Slido link for asking questions, but since this is a workshop, so feel free to just ask your questions in the live chat. And if this question is relevant to what we discuss, what we show, we'll just talk about that. And and I guess for the presentation we have at the beginning, then we'll maybe cover some questions after the presentation, right? And then there will be the workshop part. And that's pretty much it. So any link we cover, maybe Agata or Anish sent me this link and I will repost it in live chat. And I will also add it in the description. And other than that, we can start. Anish, the floor is yours.
Sounds good. Hey, everyone. Today, we're going to be talking about LLM agents, a very exciting topic that I think is front of mind for a lot of people right now. Not just including any of the craziness that's in terms of the AI hype cycles in the last weekend that we've seen and in general. But we can see that it's such an excitement around ChatGPT and utilizing it for your own applications. So I like to preface this for people who may not be familiar with like the underpinnings of how this stuff works, because we're going to get nitty and gritty into a lot of the machine learning details and the paradigms for agents. So let's start at the beginning. So LLMs, to prove to you, are an extremely popular topic. When querying the phrase large language model on RxIV, you can see that there is an exponential growth of the amount of papers regarding the topic. In fact, this number grows in an equivalent scale with just larger numbers if you change it to language model. So NLP generally, or using language as an interface to interact with the rest of the internal and external systems of the world, is extremely popular. And also like it hits this natural like sci-fi spot that I love personally. Like, oh, we're actually in an age where this stuff is actually like feasible and can be done by folks like you and me. And so people are building applications around these topics. So examples are writing assistants, information retrieval things, things for personal use, such as project managers creating bots to automatically perform actions, or commercial use like customer support, which I think is a very common use case for LLM applications that we see nowadays in enterprises. So pretty much every industry has some stake in how these language models will interface with our industry, be it in the both negative and positive lights. So I will reiterate, always approach these topics with extreme safety and consideration. Like, be your own internal risk manager as you make these projects. Naturally, as you start to play around with these things, you realize not only the faults, but also where it gets really useful and strong. And so these are both really large, like really complicated graphs. It's pretty much a demonstrative way of saying, hey, look, over the years, we've seen that these architectures that are being designed by our best friend, the transformer modules, is being really useful for a lot of downstream models being made too. So like on this left-hand chart, you'll see that in pink, that stands for encoder models. Green stands for encoder decoder, and blue is the decoder model, so the GPTs of the world. I only mention this to say that there's still a lot of interesting research that can be done in all of these different fields of modeling, and the results of these models will naturally lead to other folks using these models. So it's extremely important to understand where your model currently lies in this giant proliferation and almost like the diversification of available models that we see on platforms like Hugging Face, which we'll talk about later. But the reason this all exists is kind of three simple reasons. One, we finally have aggregated powerful enough data sets and the ability to process these data sets into forms that can be ingested by modeling processes. Secondly, for our modeling processes, so like all these like fancy architectures like GPT and stuff, we're actually able to load them onto the computing resources we have available to us. So due to things such as not only like data parallelism as implied by like the last data set part I mentioned, but the tensor parallelism and the model parallelism that we see from a lot of these new and interesting research papers, which allow you to distribute your model across all of your resources, is extremely useful too. So we have extremely high compute models with large volumes of data And turns out for this magical scaling law of data that we see right now, it just turns out that due to how the transformer architecture is scaling, and there's a lot of math stuff behind it that we can talk about. But in simplicity, transformers scale the bigger you make them and the more data you throw at it. So right now, we're just seeing that as we create bigger and better models with the proper data in like the correct format and like removal of bad data, we can see that there's this great increase of accuracy just by making bigger models. And that's all due to my this is on the left hand side, you see Optimus Prime, my second favorite transformer. This is my favorite one right here. So this one, as you'll see, this is pretty much everyone should go and read the Attention is All You Need paper and the Transformers architecture papers. There's a lot of great illustrated guides and videos. Know this. The transformer architecture is a marvel in how it really well represents the intersection between smart machine learning folks and smart computer engineering folks able to like scale this out. So transformers are great. And so the reason I mentioned transformers is, like I mentioned earlier, GPT is a transformer-based model, pre-trained to predict the next token in a document. And so I'm actually going to skip this part. We already kind of talked about decoder, encoder, and stuff. That's this in essence. This is what the model is doing. It's taking a collection of text, transforming it into its proper numerical form to be ingested by our large language model, where large language model will spit out what it thinks is the best next response. And so in this section, we use words to represent, but really we're doing this at the token level. And then one thing to mention is that just more tokens mean more computation is needed by a large language model. And one thing you'll hear a lot is this concept of context length. This essentially represents the working interaction memory, I guess you can call it, that is available to you during each message of context available to large language model when it makes those responses. And so that's really important to know, just to say, hey, tokens and context length really matter. There's this world and this word I like to use called the token economy, where large language models, especially from a commercial API usage, and even for your own servers when you like run your own like models, being able to understand how to like what the volume and queries of data coming into you for your model is essential. And we'll dive deeper into more like real use applications and how to collect that. And so in general, like what I mentioned, kind of opens up this kind of concept of because there is a lot of our tokens matter quite a lot, and a lot of users are using our data in these very specific ways. It makes you open up this question of when is it appropriate to train or fine tune my large language model as opposed to pulling something off the shelf, be it commercial via OpenAI or open source via something like Hugging Face, or you pull a model down on like create your model on PyTorch or something versus pre-training. And so I'm just going to leave this to you guys for a second while I take a drink of water. I think the self is pretty self-explanatory. Pretty much it all depends on how much investment you want to perform onto a specific architecture with the volume of data and resources you have available, which leans towards the pre-training side, where you have full control over a vanilla model, which is a good and bad thing, due to just the sheer size of data needed. And then you have the other end where you use a commercial API where you have a lot less flexibility into how you actually manipulate the behavior of some of these models. Even if you were to use the endpoints for fine tuning on OpenAI, for instance, it still lacks that true flexibility that you can do with open source models, where you can kind of unpack the model and do your own machine learning engineering on top of it and build out those interesting enhancements I mentioned earlier. Cool. And so the reason I want to mention the training and fine-tuning part is that it's really important to worry about misinformation and incorrectness from these models. So like in this case, there's like two forms of hallucination. Intrinsic hallucination, where internally the reasoning itself was wrong. For some reason, in this statement, it doesn't make sense that the daughter-in-law is Cindy is Amy's daughter-in-law. While on the other end, extrinsic hallucination is where it's due to lack of information. So it goes and makes up stuff, essentially. We have seen that before in the early forms of ChatGPT, if you've ever used it, or for a lot of open source models. And so what we want to do is we want to ensure that we prevent this type of behavior from happening. And so fine tuning is one approach to kind of remove behavior like that. And so what you want to do is you want to take your specific form of data that is specific to the task that you want to solve. So in this case, we may want to impute it with more recent information about large language model algorithms, training algorithms like RLHF. And so, or I guess paradigm, whatever. And so you would formulate that data set and you'd pass it to your model and you'd just say, hey, with the current state you're at, here's more data and just improve the network from that point. There's problems with that. And so part of that problem is it loses some generalizability to gain the specificity of that new data coming in. Because similar to humans, there's like a recency bias internally where new data just tends to be front of memory as opposed to old information. So one form of our fine tuning, though, that is effective and still maintains a good degree of generalizability is this concept of instruction tuning in RLHF. Instruction tuning is just another way of saying make the large language model, which only predicts next tokens, specifically really good at responding to instructions. So do this thing, give me examples of data, be my gym coach and provide me a workout plan for the day. So all of those are instructions that you're providing to large language model and should respond in human-like ways. Large language models are trained from the data of the internet. I don't know about you and me, but the internet is a lawless land with a lot of interesting word choices and ways to phrase things. So techniques like this ensure that we align the responses of the LLM to what humans want to understand. And so we kind of do this in a form similar to like reinforcement learning, where we kind of we cherry pick examples that are really good for what we want our large language model to act as. And we kind of we learn a policy using reinforcement learning that kind of goes and prefers the best answer for these examples, given a variety of selected answers. And then so naturally, this large language model will skew towards responses that were tended to be the most similar in style and structure to the ideal responses selected from your human annotators who help generate this data set. That's a fancy way of me saying we selected really good examples and fine-tuned on that. And that fine-tuning and process made the models that we know today, which are the chat-like models. And so one interesting thing is that now we're in this world where this concept of pre-training and fine-tuning is starting to get skewed. Now there's questions about what needs to be a significant volume of data to be kind of considered a new model. So like a GPT-3 to 3.5, like what really constitutes that kind of growth. And so I would say in essence, all these workflows, regardless of pre-training and fine-tuning, still kind of use this similar workflow for how they train their model and analyze the results of their training processes, and also process their underlying data so it's in the most available form for the large language model to learn these like language heuristics and or instruction tuning. So down here is kind of like that data workflow that you might see for at least the that you'd see a lot of tokenizers inherently do behind the scenes to really clean up your data before passing it over to the large language model. So kind of like I mentioned earlier, this kind of mixture of being able to fine tune on large language models opens up this availability of creating a lot of downstream models. So now we see like from Llama 2, which is a really popular model that we're going to fine tune on today, we can see that based on what data came in, be it synthetic data, chat data, synthetic plus task data, you have all of these kind of children arising from this mother llama that we currently have. And so that's very common workflow that you see now. Take Llama 2 and do your own version of fine tuning on it for your specific task of data. What that data looks like is what we'll talk about a little bit later too. So a little shill from us. We a lot of large language model trainers use us for good reason, I think, as someone who does machine learning for fun too. We have a great platform, which makes it very easy for a lot of these teams to analyze LLM workflows and know when it's time to press release for their model, either onto Hugging Face or to their commercial APIs. And so this nice quote from Peter Wellander, which said, "We use weighted biases to train all of our models at OpenAI. You simply can't do ambitious, expansive without best-in-class tools." What a nice statement. So to kind of look into what a workflow looks like from the pre-training and fine-tuning step, let's see, we still have time. Cool, awesome. So we'll see is this is usually the type of information that is provided to you when you train a model. It looks like an ugly log in standard out or whatever your log capturing system may be if you're using something more complicated. But if you're a little more pain resistant or you have to analyze a little bit more information than just one experiment in one terminal screen, you may want to throw all this information into a CSV. But the problem with the CSV is that you still really can't just look at this information and gain insight automatically. Like if I asked you right now, which model did the best or which model over time did the best, it would be kind of hard to just look with these numbers directly. So you may use a tool like TensorBoard or Power BI, whatever floats your boat, to create these charts itself. But then the problem with TensorBoard and all of these systems is that this doesn't really scale to the volume of more experiments. Sadly, I can say that GPT-4 and were not trained in one experiment. It was trained in powers of experiments. So a large volume of them that required you to do comparative analysis across all these experiments, across various hyperparameters, metrics, and architectures. And so because of that, we kind of came up with this centralized solution, the system of record, we call it, for your ML experiments, where you can associate any interesting tags and metadata needed to form dashboards that are really effective for your modeling workflows. So you can see here in this screenshot, I also walk through some dashboards so I can actually put my money where my mouth is. Down here, where it's a little more structured than some of the ones I'll show you later, where you can see that there's a lot of great hierarchy of how these experiments are grouped together to do this comparative analysis with good color coordination and a lot of tags associated to say, I want to look at the trained model jobs across these different groups, be it baseline 5K or baseline accessories. Look at the aggregate metrics of all that information, consolidate it into charts for loss or accuracy or whatnot, alongside different hyperparameter information extracted from the configurations from these experiments in context with the dataset itself. So things like images can be placed alongside the metrics it generated. So like for diffusion for workflows in generative AI art projects, you can look at the prompt alongside the generation over time. So you can see that transformation if need be, if things like that interest you when you're fine-tuning your own model. All this is 3 lines of code. So you pip install WANDB, you start the process called the WANDB init run, and then from there, you can log metrics, rich media, tables, artifacts, whatever. We'll walk through it later too. And the reason I want to highlight this is that when you're doing one of these experiments, even experiments, which I'm going to show you, which I ran months ago, it's really important to be able to share that information at any point. So collaborate with teammates and or the extended community, reproduce them very easily. So look at those configurations, look at those metrics, and see if I can, given the state of code that's provided, recreate that experiment. Because as the explosion of archive papers happen, so do the explosion of improper results or improper reporting due to bad systems and toolings like this. And then there's also the ability to just rapidly iterate. So I can jump back right into that project and continue where I left off, even if it was 3 months down the line. This is a cool architecture. I'll leave it for a second while I take a sip. And then we'll talk about actual use case projects, which I'm super excited to show you both the code and more slides for. I do apologize. It'll be more of a slide heavy deck in a way. A lot of this work is surprisingly linguistic and thought in nature. It's a lot of like work prompting paradigms and shifting data sets into the proper prompting workflows. But it's a very nice like insight into like the philosophical working of humans. Cool. So in essence, this we have tools to make MLOps easy and tools to make LLMOps easy. They're both related. So and I'll talk about what that relation will look like. But first, let's talk about what the modeling process looks like a little bit. I kind of walked over this. So we can skip through this. So what I'm going to show you next comes in part from our course about developing LM powered applications. This will be a light dive into it, not a deep dive at all, to kind of set the scene of what the current state of chatbots are, and then how agents come into play to replace this current form of chatbots that we see now. This talks about this first form. So RAG, the current state of chatbots. Pretty much the hello world of LM applications is building a RAG project. Taking a RAG project and putting it into deployment, now that's its own beast of its own and the true difficulty of standard software projects. And I will not be really covering that. I'll be talking about the underlying workflow associated with it, though. In essence, this is RAG that I'm showing you right now. Essentially, what you do is given a user question, what you'll want to do, so that is me saying, how can I log my inputs and outputs from OpenAI? I want to then that information is then deposited into a prompt template. So essentially, to remember back in our days of the transformer that I mentioned, well, not days, like a few minutes ago, transformers are essentially predicting the next token in a sequence. So providing this text to predict on, so pre-providing some of the text in that available context for the large language model beforehand is essentially providing a prior to that model. It's pretty much priming that model to say, oh, this is the information I currently know. So numerically, but I will predict tokens that will match what is happening currently in the state of this text as it happens at that point. And take into context the whole segment of text that was already provided due to it being transformer and attention and all that. And so what we do is we essentially say, here is the pre-written text that I have. So very generic, answer some questions about weights and biases, and don't answer if you don't know. So we plop in the question and we leave a little empty section after waiting for an answer. So that empty block of text will now be filled in with the model thinking, oh, I'm at the point where I need to answer this question given this specific, answer this question given the rules set up above in that essential system message, as we like to kind of call it. And so prompting is essentially prompt engineering, which I see that is another prompt engineering like workshop coming up from the Data Talks folk. So you guys should definitely attend that. But prompt engineering is almost its own workflow paradigm. Like I kind of mentioned in the beginning, natural language is a great interface for performing actions. And so by using proper linguistic structure and also taking advantage of the predispositions of the large language model via formatting in certain ways, you can manipulate the model to have very specific behavior. But the problem of this is that for all the extra rules you put in, the more tokens you use up, which is in essence saying per call of this query, it's going to cost more. So there's a strong balance of not using up all my tokens already for the given prompt template I have, but also ensuring that it doesn't cost too much while also having the full specificity of the behavior you want defined in this one prompt. So because of this crazy workflow, this kind of like crazy paradigm, prompt engineering is a very interesting research topic in a way. And I'll try to talk about different prompting techniques to get really good answers from large language models later. But in essence, you can improve your prompts by doing things such as add a system message, which defines direct behavior of the model, add rules in markdown or numbers that define the behavior that is restrictive of the model. So usually in an additive way, but sometimes in a reductive way too, saying you cannot do this. Models do prefer when you say you can do this, though. And so it's good to kind of formulate it that way more so, because nots tend to have a little bit more ambiguity, while saying you can do this kind of elicits a little bit more. It opens up that flexibility willingly by grounding it in a way. But that's an aside. You can also introduce examples. So in this case, we're going to be providing documents that will be relevant to this question in the prompt itself. So you can pre-add in examples of what that document looks like, and also what the perfect question answer are into the prompt itself. So the prompt at that point will include system message, rules, examples, and all the context in one file. Then you have a vector store. A quick recap of vector stores and vectors. Pretty much a numeric representation of a document or a form of data that has semantic information with it. So in the case, famous Kant's example of a king and queen, we know that they're related by royalty, but differ by perceived sex. And so sex. And in that case, what you do is if we remove male from king, and then add in a female, we should result in queen. And that's kind of what we see in this numeric representation of these documents. So pretty much this is a fancy way of saying we use another large language model to embed these documents in a way such that other related documents can be are easily linked to it. And the way to retrieve from these, retrieve the best document is by simply passing in words via natural language of the most relevant phrasing that you want to, the most relevant information that you find is necessary to retrieve a documentation about that information. So in essence, if I say OpenAI, I should get a document relating to OpenAI from my vector store, and it will retrieve it based on some specific ruling on like how to select that best document based on that input statement. We take that document, we throw it into the prompt like I mentioned earlier. So now we have that prompt with behavior, rules. Now we have directly all of the information of our documents in the prompt itself, and then my question. So now we have the information from our programming docs about this integration with OpenAI, and we also have the question about OpenAI. So we throw that all into the large language model, and we get a response. And so this response tends to be extremely structured because of all of the specific rules, examples, and the fact that we retrieve documents that were relevant and taught the LLM via the prompt how to use those documents to answer that question. But the important part here is feedback. So I'm going to gloss over the next section because the course, we have a course about training and evaluating, which kind of dives deeper too, because I actually definitely want to get to agents in the code first. Sorry, there's so much cool information to talk about. In essence, in the normal world, we kind of have this training and production distribution of data that results the ML models we use. And so whenever there's any shift of data from our test data set that we use for our final resultant testing of a machine learning model that we want to deploy to the world, when there's any shift of that against what the actual users are using against this model, you have like drift of data and stuff. But the problem is that we don't have access to that pre-training data as readily available. And also due to the large scale of it, it's hard to actually use this distributional statistics and workflows that we currently have with that volume and scale of data. And also the production distribution in itself is something you figure out. You use the LLM alongside prompts to elicit behavior, but that behavior is open to the natural language interface by your user base. And because of that you don't necessarily have that test data set, which represents that users because of that. And so because you don't necessarily have that information, you need to kind of do evaluation in a different way than we're currently used to. And there's kind of like different paradigms and costs associated with each. So you have public benchmarks, such as the LM evaluation harness, where you have different tasks associated with metrics. And these are some examples of metrics that matter. So these all relate to text. So not only do you have like overlap of text, but you can use other language models to kind of do some overlap checking. So BERT's like one example of that. And so these metrics are what's commonly seen in the OpenLM leaderboard on Hugging Face. Next, you have human evaluation, where you can hire annotators, and then you annotate the results of this model, similar to RLHF in a way, where you go back and you say, yes, this was good, no, this was bad, provide some reasoning possibility, or like formulate the data in a way so you can use that as the basis to either generate more synthetic data for training or to use that for whatever workflow to feed back into your evaluation process. So essentially use humans to make your evaluation data based on your large language model outputs. Next, you have user testing, which I think is the best form, but takes the most time, which is you talk directly to users using your product and you see how they're using it and then adjust your prompts accordingly or like generate your evaluation data very directly with a specific user test group. But the fun one, and I think a lot of people are interested in, is the large language models evaluating other large language models. So in this case, what you're doing is you're saying, hey, here's a collection of all of my fine-tuned open source large language models. Let me use GPT-4 or the latest form of whatever GPT is out to look at the outputs of all these models given the same query and given in the prompts that GPT model saying, hey, you are a evaluator of the specific model. You're checking for both objective and subjective metrics. So like quantity-based ones and quality-based ones, where you might say like, is this style of this writing good for like a creative writing versus like, hey, numerically, like what is the accuracy of this against like for Q&A kind of a workflow. So depending on your task. But as essence, you can use prompting as a methodology to use LLMs for evaluating other LLMs. Sorry, let's see if I can do this quick. Yeah, let's cool. Let's make it real quick. Cool. How this runs until noon, right? Cool.
18 o'clock Central European time, I guess, noon.
Oh, sorry. Good
What's the
call.
time for you now?
That's fine. Cool. So yeah, so when evaluating LLM systems in general, I'll be really brief with this section, I would say. What you do is you have a few examples, and then what you'll do is you'll want to just eyeball it. So what that means is, so using one of our tools called Tracer. Now let's go into some full soup maybe. No, sorry. So this is a weights and biases dashboard. There's a bunch of experiments that were run by a colleague, which relates to a mixture of evaluation tasks against large language models. Let's see. Cool. So this example of like a trace tables and regular tables. So in this case, we have table manipulations that we can perform here, where this all is metadata associated with our large language model calls, and then the inputs and outputs. So we have the true result and predicted results, and we can do things such as add expressions such as row true result does not equal row red result. Oh, that was strange. Did I filter apply? Hopefully. Darn, sorry. Live demos, you know. The Zoom thing is messing up my reloading. Okay, that's fine. Well, sorry. It was working with a few minutes ago. That's fine. But using your imagination, you could imagine that it filter out all the incorrect statements where the true and incorrect were not equal. And so from there, you can eyeball and just see which expressions directly were incorrect, and you can apply rules in your prompt to approach that, or create evaluation data sets to grab that specific behavior, so you can highlight that whenever you're training and fine tuning or releasing newer LLM based applications to the world. Or you can do things in more complicated LLM apps. Let's go back to the slide here.
And just a quick question. So here, true results and predicted results are strings, right? So this is actual text.
Sorry. In here?
It's like, yeah, because here I saw, because the expressions are mathematical, right? But I guess down if you scroll down, it's not just mathematics, but it's also like, okay, what is the longest river in Africa, right? And then the answer is Nile. And then like, this is the predicted answer, this is the correct answer, right? So so here we have strings, and then you compare strings. Am I correct?
Yeah, so in here, these are numbers actually in this specific example. Over here, we cast them to numbers. But sorry, in this expression form though, yes, they are strings. And so if these manipulations will still work, but the string matching in that case will just check for direct strings. So like, does that column's string encased in that cell equal that cell, the other column cell?
Because I imagine that for some cases, like if the answer is factual, like what's the longest river in South America, right? Or yeah, then like there's the only way to answer this question, right? But if it's okay, summarize something, then there are multiple ways to actually provide like accurate results.
And that's why the eyeballing is kind of extremely essential. So I'm going to, sorry, let's see. This is, yeah, you know what?
That's why it's eyeballing, right? Because we cannot really. It's very difficult to automate it.
Yeah, that's where the importance of let's just go back here. But so this is a more complicated example that's being clicked through right now. For more complicated, so yes, the difficult part of these applications is that because freeform text style a lot of time causes it to have the correct response, but maybe not perfectly in the format that you want it. That's why prompting is essential, and doing this eyeballing is essential too. And so like for that text you mentioned, where it's like Nile is the definitive answer, that's why things such as structured output text in JSON format and such are extremely popular now. Hence why OpenAI now allows you to use pydantic models, and interesting packages like instructor exist, which allow you to define that structured result so you can immediately capture that in a more structured format in like a CI pipeline. Like, oh, this key doesn't exist, therefore it's like a failure, or like it's missing some sort of elements regarding that. And the second part, which I also which was mentioned earlier, the LLM evaluating another LLM is another way to capture that. So it's pretty much just saying use an LLM to be your eyeballs to perform those actions. And so that's like extremely both those together hit that qualitative problem where a lot of this stuff is just intuition.
So the prompt for evaluating could be like, this is the predicted answer, this is the actual answer, like do they match?
Yes. And then from there, it could be like, so there's, you have to be more specific, like, does it match from an accuracy perspective, or are these semantically related? Would you say that these two responses, given the previous context, answer in the right way? Like, there are ways to really, so that's like a big research problem in itself. Like,
so there's a lot of prompt engineering too.
Yep, exactly. And that's why part of it's also still for the evaluation agent you're making, you can't even really give a generic one. It's really dependent on your task and use case, because sometimes you do want to not just be like a generic QA checker. You might to be like, oh, you check financial records on my earnings every month. Your evaluation is way more specific for certain actions. You may apply penalties, for instance. I've seen like a penalty-based approach in evaluation, for instance, where you say like, if this exists, then remove a score. That's the overarching score for strings and stuff. So a lot of interesting ways to like generate scores which represent that qualitative example. So yes, prompt engineering is essential. Maybe I'll skip through some of the stuff. So we kind of talked about some of this. So eyeballing is just like use your brain. Supervise is kind of like use a mixture of qualitative and quantitative. So like have numeric metrics that we can easily calculate, similar to what I showed earlier. But at the same time, also ensure that you have that similar ability to eyeball. LM, LM, this is the cool one. This is where you can do things such as here's 3 different templates for prompts I want to test against my main application. So the one performing mathematical expression against things such as different models, different temperatures, and different value, these different prompt templates you see here. And so what you will do is you can gain those qualitative metrics and check your hyperparameters. So that's, you can see that here when we go to sweeps and we go to math sweeps, we can see that this chart, oh, it's not as nice as his. Can I switch to his thing? Sad. Okay, well, I can adjust this. I'll do maybe. Let's see. In essence, though, you can put the context of your metrics with your hyperparameters together in one chart to do that hyperparameter tuning. And in this case, we still have access to things like that grid search capabilities. So we can literally plug in different LLMs we want to test against different templates and have that automatic flow where we can calculate those quantitative metrics similar in a supervised based approach, where it's like, what is that raw accuracy or F1 overlap? Or you can have the other side where you have that final accuracy where you might have, we don't have it here. I don't think we do. Oh, that's not it's not a measure in this one. But we have also, you can just have a separate accuracy measure in a way where it's the LM based eval accuracy. And so you can check against all those different hyperparameters and configurations.
There's also a question from Martin that to measure the matching level, do you use cosine similarity? I guess that's one of the options, right? So you create an embedding from the predicted answer, you create the embedding for the correct answer, and you then measure the similarity between the two, right?
Yes. So there's this measure here. BlueEarth is that. So if you ever see that BlueEarth statement, that is using BERT to do that semantic consolidation, I guess, into an embedding and then doing the overlap. So yes, that is something you can do, and that is a great measure. If you do want to see which data sets exist with that, I would really encourage you to check out the LM evaluation harness. And just search for BlueEarth. There's a lot of this harness allows you to check your LM against generalizable data sets for scores like BlueEarth and whatnot. But great intuition. That's exactly what you do. So cool. Yeah. So this is the LM eval kind of hyperparameter way of like approaching how to use these like the generated quantitative metrics to select the best model. Cool. We've used all this feedback. So now what we did is we had this workflow in mind. Okay, I'm going to eyeball to create the better prompt, which I showed earlier. Now I'm going to do is use the user feedback itself, though, so these numbers, to generate a good data set that will actually represent what the behavior is that I want to evaluate over. So it hits all of the different topics that come up from users. So to recap, this bot is specifically to help users with weights and biases related queries. So we gathered all the information from positive feedback. So that's thousands of questions, and we used the standard. So right now, a lot of you data science folks or regular data folks will look at this and go, that's not machine learning engineering. That's just software engineering and data engineering. Because it is. What we do is we essentially take all of our questions, we do some topic modeling to ensure we create clusters of different questions. And then we take each of these clusters, so testing out a bunch of different clustering algorithms, different ways to like build these graphs. And we just randomly select one question from each cluster, which will represent a topic that will represent the kind of the breadth of user queries coming in. And we take that data set and we run that LM eval. So in our case, the 2 measures we looked at were faithfulness and relevancy. both of which are slightly different from the core accuracy value. So faithfulness is saying accuracy as given by the document provided, while relevancy is does the answer respond to the user given given that context. So one cares about correctness and connectedness to that context itself without external information, and one still is like using its underlying reasoning alongside the user query and the context to answer that question. This is kind of an interesting measure, but I think it kind of hits this. It is a variant of accuracy that can be slightly more consistently reliable by large language models. It is very easy for us to say, oh, just tell it to tell us how good it does. But if you're not very specific about how good it is, it may easily hallucinate or make it up if it doesn't know. So faithfulness and relevancy are more clever ways of using LLMs to say, hey, you have access to all of the pieces of information to actually respond to this version of accuracy. We as humans could theoretically also create this, given only the question and context and response, for instance. So like, for instance, that question, context, response triplet is something you'll see quite a lot of, as that's also the core, a lot of these fine-tuning data sets that I'll show you. Then you have us sitting down in a room with a tool. I forget which tool this is. Is this Prodigy? No, it's not. It's Argilla's, right? Whatever. We use a tool for annotation. So we sat down and as human experts and machine learning engineers and weights and bias employees said yes, no, etc., and helped curate this data set from that small 132, and also make sure that we can compare against the faithfulness accuracy, relevancy accuracy with like normal human people accuracy. And this also allows us to capture gaps in our data set itself. So like, for instance, when there's missing information in our documentation, or if there's hallucinations, we can also capture that a little easier. So mistakes in links are very common, or just like code snippets that seem correct but aren't correct. So we can take all that information and put it right back in that prompt. And so, yes.
So this the results from the evaluation. I'm just trying to understand the flow. Like, do you put it back to the training database, the data set, or you put it in the prompt, or how do you use it?
Depends on your workflow, and I'm just
like in this particular one for you, like, because there's a question from Hussein, and I was wondering about the same thing. Like, do you add your evaluated data set to your actual data set if you get the evaluation section?
Yeah, so to remember that this is a large language model. So we don't have access to that pre-training data. All this data that we're using.
It's OpenAI, right?
Oh, sorry. In this case, yes. Sorry. In this case, it's OpenAI. Yes. Sorry. Like for this specific example, what we do is that we use OpenAI and just generate this data set for evaluation. But we are investigating using this with fine tuning. Like we have fine tuned on the GPT 3.5 interface. So essentially, the evaluation data set can be transformed and used for training later. Not to say train on your eval data. It's more because of the fact that this is not a straightforward task you're solving for. You have to treat this more like a standard software project in a way, where you build an MVP to generate kind of the representative data, use the learnings from that to either say, I want to specify more strict behavior to generate better data for my users, or generate that better data yourself using those human annotators to feedback in the loop. So in our case, we already condensed using topic modeling all the questions down to that cherry pick set for us human annotators to then annotate on, which we then use downstream for fine-tuning experiments, which we'll then use against the other range of questions that we didn't actually go ahead and use, for instance. So like subsetting your evaluation data set just for like really good gut checks is like very standard machine learning EDA kind of. It still feels like EDA in a way, that exploratory data analysis. But the problem is that we're exploring data coming directly from this model against the model itself. So it's like a 2-for-1, evaluating and exploring at the same time. And then yes, we will use that for training, and I'll show you what that looks like. Because this use this workflow is very interesting. It's under the name of distilled GPT, if you've kind of heard, where you use GPT outputs on other large language models or even GPT 3.5 to make GPT 3.5 more like GPT-4. And so that is like one workflow that you see commonly. One that I just want to highlight on this slide is serving everything I mentioned, like again, is a lot of data engineering and a lot of software engineering. You hit an API. As a machine learning engineer, we're in the seats of OpenAI usually. So we're the ones who create that API service on the left-hand side to be used, sorry, not on the left-hand side, but to be used in applications like this, where eventually you can serve it on Slack, Discord, and API. So join us on Discord if you want to try it out. We use it all the time. A lot of users tend to like it, even though it does have mixed results here and there. You all make great training data, supposedly. So cool. Okay, let's speed through some of this. Cool. So one thing we're going to see now is, though, throw out everything I said right now. What instead we might want to do is, instead of saying RAG itself, use LM to do one specific action given context itself. We as humans have defined all of that behavior. Agents are interesting because they all this behavior in itself is selected by a large language model. It is looking at the situation presented by a query by a user and selecting the best plan to then approach solving that query of task. Be it, hey, I'm going to implicitly select how to think about this problem before actually applying that thought process on this query itself. And so I say that very explicitly because you'll hear about things such as chain of thought, reflection, and tree of thoughts. Very cool prompting paradigms. This diagram is very useful, where this top part here, this right here, is still that WANBot RAG that I showed earlier. But now what we did is we made this one available part of the tool from Wand Agent to say, hey, what I'm going to do as an agent is pull the most relevant documents, but also I'm going to take those most relevant documents and decide what I'm going to do with them. Either write specific WandDB specific code or use some other tools to help refine this initial collection of information that came in. So that's what agents are kind of good for, is this kind of triplet of actually, I'm going to hold it for a second and talk about this first, and then we'll go into specifics about how agents are broken down. So what you'll see here is an example called Wand Agent. So Wand Agent, essentially what it will do is it will go ahead and use that workflow I showed in that slide. So it has a mixture step of grabbing retrieving the most relevant documents from a vector store. So in this case, this tool represented in green says retrieve this information from our doc store. Then, given this information, we have now specified, soon blah blah. This defines the system behavior of the AI itself, the one that's doing all this planning and reflection. This is a list of tools. Actually, let's full screen this for a little ease. Let's zoom in for folks like me whose eyes are failing. So over here, I'm gonna do this. Cool. Not the agent executor. I want to get. That's okay. Whatever. Important part here is saying you have a system message, you have your rules, but in this case, these rules define what tools are available. So the tools available are WANBot to query our WANBot service and grab the most relevant context or answer, code generator to write code, or a mixture of these tools. And so this defines what those tools do and how to utilize these tools effectively, and opens up this kind of It's a lot of rules we had. And also defines rules saying you're an open AI, you are a tool, you have memory, and at any point you can go ahead and use context alongside your thought process to go ahead and decide the best answer. So over here we can see that we actually, so this knows to use the highest accuracy tool. It gathers that context to grab more date context, it looks like in this case. So for some reason, it queried the service twice. And then it took both these documents, it seems, and created an answer. So this is like one way to do eyeballing. And all of these workflows look slightly different if I kind of paginate through these outputs. You can see here that there's a kind of a collection of time it takes to answer these responses, and also the amount of steps needed underneath the layer of the agent to actually provide the answer that you see on the screen. So from a code perspective, so one cool part here is, for instance, in one individual experiment, I can go to the overview tab. Oh, it crashed. How's that? That's fine. You can see here a lot of different information regarding git state, Python, CLI version, job type, CPUs, etc. So system information. I'll show you what the GPU information looks like soon. We can also do is see configuration. In this case, there are no configurations. We also see here this git state. So I can see this comes from the WandDB wand agent repo. So if I go to GitHub, I think this is going to work. Yes, this will open with the wand agent repo. So very easy to like have that one central place. Because in this example also too, this was ran a month ago. So very easy to still retrieve all this information. If we look at the code itself, also sadly all this code I'll be showing, a lot of it is still in work in progress. So the shareable collab piece I'll still send over when we get to that point. But regardless, if we actually break down the agent, we can see that loading the agent is essentially saying, sorry, it's not loading. Load agent right here is essentially very easy to like create agent in using frameworks like Llama Index or LangChain. You define that you have memory. In this case, we have token buffer memory. So clear out your tokens by using smart ways to whenever there reaches too many tokens inside of an agent context prompt, for instance, where eventually you're going to need to throw out old memories that were injected into the prompt because it's going to take up too many tokens. You have tools, which are, in this case, that code generator and code interpreter that I showed you earlier. In this case, we define an agent prompt based on the agent itself, and then we make that agent based on the LLM that we define. In this case, the agent LLM we chose is OpenAI's GPT-4, but this could honestly be a lot of different agents. When you use a lot of these frameworks, I would definitely say after the events of a very tumultuous weekend, it's very important to ensure that you have a stable interface to be able to communicate with a lot of different LLMs and not just one provider itself. And then you have the agent executor, which actually is what you will query to run the specific agent. So in this case, all of this is essentially like 20 lines of code, where a big part of this is this description is what is injected into the prompt for the prompt to know how to use this specific tool, and similar to this. So in this case, what you can do is one thing you test out is not only your prompts, which is obvious, but also the descriptions to your tools to make sure your prompts utilize these best descriptions. Cool.
Is it a private repo?
Sorry. Ooh, screen share ended. Sorry about that.
So I was trying to find this repo while you were presenting, but then it doesn't seem like
it's not open yet. So yeah, we'll be releasing this soon. Sadly, yeah, early sneak preview of this specific one. But yeah, so we'll be sharing this soon. But that is essentially the core of this. There's like little accessory functions to like load certain tools a little bit better or to like format things, which when we share this is useful. But I would say this workflow from a application development standpoint, so like as the LLM user, not the fine tuner or trainer, this is what all this looks like to me as a creating an agent. I want to simply say, hey, I'm an agent that can do multiple things. In this case, the functions part is also important because it can like call functions or like read a function that you define and define the arguments that it would pass into that function. That's called OpenAI function calling or general function calling in general. All of that information is like super is useful for users who are developing these applications. But now let's get to the fun part, the one I really want to show you guys. So instead of saying, hey, can we improve the processes around the prompts, the tools, all this kind of like token management and like API management in a way, what if we instead use all this data that we're collecting from our user interactions from evaluation and whatnot to actually train and fine tune our models? So remember, tokens cost money. So tokens are not one-to-one words, and more tokens mean less space for responses and less space for you to drop in context for your model to answer.
And tokens are usually words or characters, or how does it work?
It is 2/3 of a word. It's a very specific way they calculate tokens because there's like, yeah, it's a tick token is a very popular package. Transparently, I don't really remember how the heuristic for their token thing it does. But the reason they do that is there's ways that they like consolidate tokens in a way for an LLM that still has like still represents the original text, but also like is like token efficient or whatever. I don't know any of that stuff. I'd recommend looking at tick token, the package. That's the package that helps you pre-tokenize all of your text into tokens for these types of calculations for OpenAI costs.
I see it says that there are 9,700 characters and only 2,182 tokens, right? So it's apparently not characters.
Yes, yeah. It is, yes, mostly on a character basis. So like I think it does not overlap spaces of text, but words can be broken up into smaller logits that are for some reason more token efficient to process.
Okay. TikToker.
Yeah, TikToken, yes. Cool. So recap again. RLHF was that algorithm, that paradigm to ensure that we have chat-like behavior from our large language models. So the chat GPT that we see now is GPT 3.5 and or 4 fine-tuned to be chat-like. So that's like the caveat here. But there's a cool thing here. The cool thing here is that you can learn RLHF from an RLHF model. So in essence, because GPT-4 has been so very nicely fine-tuned, maybe we won't use one that breaks terms of service, like well, it has HCM service, but let's say you have like a really good chat model from like Hugging Face that you pull down, and you have a base large language model that has no chat capabilities yet. You can use the data from the model that like the model that's been fine-tuned for chatting. The output of that data will inherently will make the model that you're fine-tuning have that chatting capability. So in essence, like the small way to think about it is you can steal RLHF from other models by using their outputs because those outputs have already been optimized on the most optimal responses from a user. Similarly, you can also just generate that data set of here are the optimal responses given one query. Here's like the different varieties that are all considered really good from this model. So that's nice to hear that you can still take some of the underlying capabilities from these other large language models, and this data doesn't need extremely significant processing to maintain a lot of its instruction formatting in a way. To come to this point where you want to structure your data set in ways that are able to be instruction formatted still. So not to like kind of repeat my phrasing. Pretty much you want to ensure that you're able to break down the input text into very specific formats So your large language model is able to take requests of that format or condense incoming requests into a format like this so that it can actually solve your query efficiently as opposed to hallucinating or giving out garbled text. So let's say someone gives a large block of text that's about like weight loss for some reason. Instead, this might look at this block of text and really condense it to that task of, oh, they want to know recommendations for how to lose weight. And then that, because it knows to consolidate that original unstructured text implicitly into a task form, that's like really useful for us. So traditionally, when we fine tune, you may say back in the day, it was if you train a small model of parameters, sorry, small volume parameters, usually result in a worse model than adjusting all parameters itself. But the creation of parameter efficient models, especially with large language models, break against that workflow. Smaller models struggle with being able to match smaller parameters against the full parameter fine tuning. But because of the large volume of large language models and a lot of interesting research, which points to during like inference time and whatnot, there are a lot of modules internally of the model aren't utilized as effectively, for instance, or like only activate in a certain specific ways. Because of that, we can have this parameter efficient fine tuning where we do select a specific subset of parameters within a model, or we train accessory models, which will be able to be used alongside the original large language model. So like in this case, in step 2B, for instance, this is a more of a p-tuning type of fine tuning where you train a separate model alongside so you take the unstructured data that you have, you pass it into the model to get responses, and you also have a separate fine-tuned model you have a fine-tuned model which will take you have a fine-tuned model which generates these tokens, and these tokens represent a task that is best used by a large language model. And these tokens were learned during the process of fine-tuning against the instruction data set. So like in the case of question answering, you might have to write this giant paragraph about like, you're an AI for question answering, et cetera, et cetera. It might make sense to throw away our human understanding and think in the data machine learning realm and say, let me build a small 4-token representation of my task that makes no sense to me, but makes complete sense to the large language model, such that whenever that's prepended to my input query, that's full prompt of those 4 tokens plus the input query will make the model inherently know, oh, this is the tokens that represent me being an AI model specifically for question answering financial documents, for instance. So that's p-tuning. The popular one, though, is LoRa, where instead what you do is you create separate weight matrices on targeted modules within our transformer architecture in a very mathematically efficient way, such that these weights are applied onto the model kind of during runtime and because of that, that manipulates very minutely the internal like numbers of the weights of the original model itself, which then allows you to essentially what it does is it prevents the original full model from necessarily being from fine-tuning itself. So you're not adjusting the layers directly from the model itself. What you're doing is you're applying new weights so that new weights represent that change into the task that we care about. So instead, what you would do is instead of having these different tokens in the prompt which represent your task, you have weights called adapters that represent the task you care about. And the future we see now is a lot of people saying you can have a whole model registry of weights, and each of these weights can be easily hot swapped during runtime, depending on the task you care about. So one central large language model, a bunch of different task-dependent weights. Here, the user query, swap in the proper weights based on that task. So LoRa is really good. It's almost as good as full parameter. And so time permitting. Wow, sorry, there's so much information. So this collab is open for folks. I'll drop it here. This is a traditional fine-tuning one, not with agents specifically. But this takes the concept of using quantization, Hugging Face fine-tuning, and a standard data set. We do it on a smaller model, OPT 125. You can throw in a bigger model. You will have to change the tokenizer and some of the workflow a little bit. But we want this to run on a free T4. I think for free T4, yeah, free T4 GPU on Colab. So this is kind of the setup we have. This uses different tools such as bits and bytes to load in smaller forms of the model that will reduce in size and complexity by reducing the precision of the numbers for these models. So as opposed to floating point 16, we have floating point 8. And later down the line, at the end of this notebook, you can take your final model and quantize it further into floating point 4, I believe. Oh, sorry, it was floating point 32 into 8. So reducing it by a large volume of parameters. Then what we do is we apply LoRa. So LoRa is really easy to use, nicely enough. In the current state of the large language fine-tuning world, you simply define a config and in the target modules. And this will say, okay, gonna build a model which will generate these weights for these specific modules. And this means that in our model originally, so you'll when you print this out, so we have it, I don't have it run. It's okay. Sorry, see the workspace. Yes. One cool thing is we also save states of your code. So cool. No outputs. Curses. Okay. Sorry. So what I'm showing right now is the code tab of the weights and biases dashboard. You can save the state of your code as you use it in dynamic environments like Colab or from directly your code snippets. So you can easily see the state of code as it associates with configurations and other model details that you want to save in your dashboard. Oh, it's gentle. This, I think, and going here, here. Yes, look at me. So I'm gonna print up. That's it. Fine. I don't want to take too much on this. So over here, you'll see that it'll show you how many parameters you actually get. You only need to train. So originally, it would have said 125 million. Sadly, it's not printed here. But it will say after adding in this, the amount of trainable parameters reduces to I think only like 70,000. So there's a large reduction of parameters as this LoRa config will look at all those targeted modules and say, and we as the modeler will freeze the rest of the model itself so that we only use the frozen parts for forward passes, but we don't update on the backward pass during this back propagation training process. We use our great transformers package over here. Thanks, Hugging Face folks. And in this case, we use English quotes because we want to fine tune this OPT model for being really good at Shakespearean quotes and whatnot. So this workflow is effectively the same across the board from Alpaca 7 billion to Llama 70 billion. All of these workflows are essentially the same, where you can adjust these training arguments to change things such as floating point or the amount of steps. I highly recommend reporting to WANDB so you can actually automatically capture things such as your checkpoint, your metrics, and your configuration. So to kind of go back to this specific experiment, you can see that this captured automatically all the configuration. You can see the system utilization here. Oh, this one didn't save properly. I'll show you one that's worked. You see all the metrics as it's saved to. So the loss values and learning rate and any other associated metadata that you care to save. So in this case, we save those and also the checkpoints. So we have this thing called artifacts, which allows you to save essentially similar to a bucket, any form of blob of information. So in this case, this file coming from these checkpoints literally holds those adapter files I mentioned. So if you see here, the original size of this data set, this model is only 7.2 megabytes in related to what I believe is the 1 gigabyte model that was the original OPT 125. So this is really effective because you can save a large volume of adapters for a fraction of the original model space usage. But cool. Sorry, here. So looking at the artifacts. So we can save those artifacts here too, automatically. Then all you do is you run the trainer. So you instantiate a trainer.train transformers trainer. You pass the model, which we loaded in here. In this case, the only changes you'd make down to these two is changing these to be the model you care about. So this could be llama, for instance, if you want it to be llama. Just make sure you read the documentation page to see what flags you kind of turn on or off, a lot of configuration stuff. Then you simply train. So in this case, we run trainer.train and want to be finished when we're ready to be done. And then once we're done, we also have this extra step here, which I'll let you explore on your own, which will take the model we just made and quantize it further for, I believe, yes, to half precision. So reducing our taking our original 16-bit model. No. Sorry, I think this quantizes down to like 4 bits only. So this I'll leave you to explore. But essentially, this takes the concept of take your model alongside its adapters and even further reduce the complexity of the precision of the floating points so that it submits on even smaller devices like edge devices and whatnot. And for us, we're actually able to, what we create is kind of model registry here, where we can then take the best model that we care about and give it a name. So whenever we want to use this model, all we have to do is run this line of code and it'll automatically access all of this information in here regarding our parameter efficient fine-tuned model. So cool. I will be brief with the next part. So now finally to agents. Sorry. Oh, this is the back half. So all of that was to say we have RAG, we have independent agents. We're able to take the outputs of both our agent and LLM pipelines, evaluate it properly using qualitative and quantitative metrics, and then feed that back into a training pipeline so you can use parameter efficient fine-tuning over these large language models to get that task-specific behavior based on the outputs of our application as we made it. That's the current workflow as we see it. Now to the future with agents. So agents, as you can see, also are seeing kind of this meteoric rise in the popularity amongst the research community, where we're starting to see language agents being used and investigated for a lot of different use cases generally. One thing that's important about agents and modeling in general is that because the pre-training split for a lot of these models vary across the different internet scale data sets that were used, the underlying reasoning thought processes of these models differ. And also this also is extremely important for agent use cases, as this widely varies agent behavior. As within LLM RAG behavior, we use prompting as a mechanism for restricting the behavior of agents. With agents, what we're effectively asking for is flexibility within decision-making processes, but with caveats that we set ourselves that we may not even know are available until they occur by the agent. Agents themselves are broken down into this kind of like framework of planning, I like this one a little more. Planning, profiling, memory, and action. I'll walk back this later. So profiling, in essence, looks at the underlying context and data set to actually answer possibly a query. Memory, what it does is it uses things such as vector stores to save those profile data sets, or in the chat existence of its own, while it's being used, it may also need to consider the concepts of short-term and long-term memory, where you want to be able to use short-term memory to grab most relevant documents and the context of the current existing conversation and maybe relevant other conversations to answer questions. But while planning looks at planning is long-term memory, where you're trying to look at and say, okay, in the existence of thousands of conversations and thousands of code generation plans, I want to select and ensure that I improve myself and plan for the future. So in this case, it might say for like a chat dev, for instance, which and generative agents to papers and I guess simulation simulacra, which specifically look at the behavior of releasing fully autonomous agents with internal heuristics and rewards and telling it to live on its day-to-day. So use that profiling of memory to like exist and optimize its scores, but it also optimize these scores in the long term. As for instance, like one behavior you might have for an action in a video game that you're making, is you might have them consume a candy bar to gain happiness and fullness, but reduces the health stat. Short-term benefits may occur, but in the long term, that might affect the long-term longevity of that agent success as it looks like in the long-term plan. So that's like one effective part of agents is that long-term planning generally. And last part is actions. So using its plans, its memory, and available context and information coming in, it needs to actually go and do things. So it may actually go and respond to that user in the most basic form, but might go ahead and actually use its plan to generate more plans to then be able to go ahead and use the memory and profile information to go ahead and use a tool, for instance, search Google and gather more information to then further its own plans or retrieve that final action of responding to the user. And that's what kind of this shows here, where there's this environment that exists. Internally, the LLM is making decisions called like the thought processes and reasoning overall. And in the external world, which is us providing that input prompts and is screwing up its nice digital world.
And external could be file system, right? Because there is a question
yes.
from Martin. If an agent can interact with the file system, for example, we have a bunch of PDFs and we want the agent to look at these PDFs and let's say tell which ones are relevant.
Yes, agents can in essence, this one of my ex-colleagues, Charles Fry, has a great kind of paper talking about LLMs as OSs. LLMs in essence can do anything that we as humans can effectively do. And especially from the internet paradigm of the world, this is extremely true. As within the real world, obviously, most robots can't pick and lift things unless you're like one of those crazy Boston Dynamic ones. But in the internet world, agents can be programmed to have the capability to connect to the internet, to connect to your final system, to connect to an IDE and automatically deposit code that it runs for you. It can automatically connect to VS Code and generate plugins and themes and whatnot. If you can programmatically do it yourself, an LLM can do it.
Yeah. So essentially, if you can express what you want in Python or JavaScript or some other programming language,
yes,
then an agent can do that.
Yeah, so in a way, I don't want to like make too many assumptions. I think Charles is a way better than I. But like LLMs in that OS kind of mindset is able to compile our human text into the proper underlying data machine format, which then spits out the next collection of information to then actually perform those actions against the tools that actually use it. So that's essentially other processes in the eternal LLM agent OS that's occurring. So yes, this LLM can do a lot of capabilities. And so that's really cool to say that this is all occurring because of all of this information, is being really scrutinized. And so the black box of an LLM agent is being unpacked by using clever prompting. Oh, okay, super speed run. Sad, this is the really cool part. So React is reasoning helps acting. So in this specific paradigm, what we're trying to figure out is how well is the LM agent actually able to articulate its thought process so we can ensure that it performs the best actions. So what React does is we create this kind of reasoning trace, reasoning and acting, which represents the based on an action provided by an LLM, we look at the result of that action, and then we use that as the data flywheel. So do we have an example here? No, when we look at the example, I'm gonna look at the example first. So like in this case, if we just say, hey, use straight up your own LLM wording, underlying reasoning to answer this question, it'll do incorrectly. Sorry. Yes. So in this case, because it doesn't necessarily have actions, it doesn't go ahead and actually search for this information. Is going to give the incorrect answer. So instead, what you do is you provide the actions it's able to do, and in a very consistent format, where this is the React structure here, where you have the action, in this case, search with the query and the response from the query, and then you sequentially generate this kind of information. So this is the chain of thought kind of process. And this is really nice because this gives us a data format for us to define how to structure long-term thoughts and short-term thoughts so we can specify how we want the LLM to think. So by adjusting this data set, in essence, you can fine-tune your large language models to have better agent behavior. So this, in essence, React is good for short-term memory. So it's saying here in the short term is answering one query. Then we have reflection, which is what it does is it has a long-term, kind of this longer-term database of information, where what it will do is it'll know when or not to save short-term and long-term memory against maybe like external data store and be able to use that to think about the long-term process. So instead it'll say is, hey, not only will I say thought here of like what actions to do, also provide an action called thinking pretty much, which will say, just think about the current state of information and plan what you should do next and then perform those actions. That's what reflection kind of points to. So it opens up a long-term planning as a capability. And lastly is tree of thoughts, where what you essentially want to do is define different variations of thought processes and thought chains that a LM can take and define ends and not ends. So in that case, what I mean by that is what you'll do is you'll say, here are all prospective paths where you can take. You decide the best path and then continue on that path. So the tree of thought allows you to have a lot more flexibility at the cost of by having more possible responses at the cost of more tokens. So using all these together, you kind of have this paradigm against reinforcement learning agents and language agents about how you plan, learn, and perform actions, but they still have this very good paradigm together. And so super quickly, this opens up a new world of using data to generate more data that can be used to fine-tune your agents to be better at the agent information it's particularly good at. That's the current age of large language models and agents itself, where it's like learning new tools automatically or selecting best tools for certain situations. And this happens across all industries, where there's a bunch of different agents that currently exist now. And so combining all of these different methodologies alongside that structure of React earlier is this project called Fire Act, which I was able to I'll share the code later. This is not a runnable code very easily. You need an A100 for sure. But in essence, this uses a very similar format to the fine tuning I showed you earlier, but specifically against the Hotpot QA dataset with this specific React framework that I showed you earlier. This structure of text that you see here. To show you quickly what that looks like from a experiment point of view, you can see here the table of information of, so in this case, what is the prediction and ground truth? What is the trajectory of thought process that I fine-tuned on? So we can see here that it actually goes ahead and knows what to search and how to use that search information. And we can see that in context during the training process. So during training, we can see the evaluation metrics and training metrics over time. During training, we can see for each step how well it actually did. So on step 3-100, it had this really weird text, which may not mean a lot to us, but internally does pretty good. But when we look at step one, it has even worse text than that specific jumble that we saw earlier. Ooh, so like in this case. So this has a lot more jumbled text. So I'd like to thank all of you today. Hopefully some of that agent information near the end stuck with you, but hopefully I was able to show you this full process from one LLM to RAG-based pipelines to evaluating good LLMs workflows, then taking those workflows that we learned, use it for fine-tuning, take that fine-tuning, apply it to the thought processes of these agents, and realize that fine-tuning LLM for an agent, which just has more tools and planning, is the same as fine-tuning normally. It just requires a slightly different data set. So perfect for the data talks, folks. Data is extremely important and will always be the core of all of these cool models. AI is data-centric. Thanks, guys.
Yeah, thank you. There are a few questions that we sadly don't have time to cover them, but is it okay if folks contact you via LinkedIn and ask them?
Yeah, sure. And
So
if I'm okay to stay on
track.
for a little if we do want to answer questions, but I don't want to keep folks over either.
Yeah, I kind of need to go. So
Oh, that's totally fine. Yeah, feel free to send it over,
but,
and yeah, let me know your
yeah,
thoughts and give any feedback. This is one of the first times we also do this agents talk, so I would love to know more
and
about.
also a few seconds ago, maybe a minute by now, there were two links for Slack and Discord, and I
Yes,
assume
let
you
me
hang
send it
out
over right
there
now.
too,
Yes,
and you can answer questions there, right?
yes. I would connect with me on LinkedIn or go to these two
Yeah.
resources. Discord is our community, and Courses has all the courses I showed you earlier, and we can
I
definitely
will
work from there.
put these links right now to the live chat.
Cool.
And yeah, so the links are there. And we will also, I think the things are kind of messed up, but yeah, you can make sense from them. Yeah, and that's it for today. That's all we have time for today. It was amazing, like a lot of information. Yes, probably we will need to rewatch it to kind of regurgitate it one more time. But a lot of information, very useful. Thanks, Anish, a lot. And thanks everyone for joining us today too. And I learned a lot. I'm sure everyone also learned a lot. So thanks a lot for doing that.